Okay, welcome to the Artificial Intelligence webinar at the University of Maine. Good morning and good afternoon and good night, no matter where from everywhere in the world you're joining us. I would like to start by thanking our sponsor for this event, IEEE at the main section, as well as IEEE Region 1, IEEE USA, and our colleagues in IEEE Silicon Valley area, as well as IEEE India and IEEE China. So thanks everyone for joining us. Today we are having 4 speakers presenting new seed grant research ideas in artificial intelligence area. And without further ado, I will introduce our moderator for the day, Dr. Saul Allen, Associate Director of Office of Research Development, who have been managing these seed grants. Just make sure that everybody is aware that there is a Q&A button at the bottom of your screen, so you can post your questions there. We'll have all the 4 talks first, and then we'll have some time for question and answer. So thanks very much, everyone, for joining us. And Saul, take it away.
Yes, to echo Dr. Abedi's welcoming remarks, we are delighted to have folks joining us today and to hear about these very sort of exciting projects that have been underway for almost a year now. And so I don't want to belabor the point, but I want to provide an introduction to each of our speakers and then let them characterize their work and their progress to date. So first, we're going to hear from Dr. Sepida Ganavati, who is an expert on privacy and security and software engineering and has active research program in regulatory compliance, IoT or Internet of Things privacy, and is going to speak to us today about a multidisciplinary project titled Advancing Legal Technical Approaches for Protecting Privacy Rights and Civil Liberties in the Age of Big Data. So I'll turn it over to you, Dr. Ganavati.
Hello, everyone. Thank you for the introduction. Today I'm going to talk about the project that we have, which is called Advancing Legal and Technological Approaches for Protecting Privacy Rights and Civil Liberties in the Age of Big Data. In this project, our PI is Dr. Harlan Onstrud, and I, together with Dr. Worsdorfer and Dr. Chen, are the co-PI of this project, and we have some collaborators from UMaine Law School, Dr. Peter Guffin and James Campbell from the Maine Freedom of Information Coalition. This project, we broke it down into 3 pieces, and we basically, the core of all of these projects is to provide techniques and measurements and approaches to protect privacy of individuals and making sure that developers have enough tools to support creating privacy preserving application in the age of AI and machine learning and big data. These 3 projects I'm going to briefly talk about what we have done so far and where we are going from here. The first one is called PriGen, which is a neural machine translation framework based on deep learning, which its goal is to generate privacy statements from Android source code. For this, we break it down into 2 pieces that we identify and classify purposes for collection and processing of personal information and identify the privacy practices of Android applications. And we also then use deep learning techniques to automatically translate these pieces of codes to privacy captions or privacy statements. The other one, FIN, which is a privacy protected heterogeneous Internet of Things network, it basically tries to make user aware of what are the privacy risks of an IoT device when they are in a network of IoT devices in a smart home environment, and also providing a platform for privacy negotiation between the IoT devices and the users. And finally, the privacy aid, which tries to evaluate social network applications and I don't understand that how much they are misleading or misguiding the users about their privacy practices, and see at what are the privacy behaviors of vulnerable population of the society related to these social networking platforms. And the reason that we are talking about these 3 projects, that all of the students that are working on these projects are getting funded over the summer period from this AI Seed Grant. I'm not going to go through this complicated overview. I'm going to explain details of it in next slides. The only thing that you need to know is that we have like several collaborators from Google Privacy Research and Dr. Colin McMillan from University of Notre Dame, Dr. Peter Goffin and Dr. Roy Turner also work on this project with us. And we have several students from undergraduate and PhD students that collaborating on this project. As I said, the goal is that to identify which part of code in Android applications are related to permission requiring code, which basically collect or process personal information, and then translate it to a privacy caption. So this piece of code that we identify through our static analysis tool gets translated to, we collect their precise location and share them with third parties. And we have done some studies on this, and we have already published a paper related to this work. As I said, for identifying the permission requiring code segments, we developed an in-house tool, static analysis approaching tool, which you can get from our GitHub page. And this tool basically identifies where in the whole application, Android application code, they are requesting to access to personal information, what are they doing with it, and who they are sharing it with. So we collect those, and then we use some deep learning model, which is like code to sequence, to generate these captions. We have so far downloaded 80,000 applications from Android Zoo collection, which has like more than 1 million Android application APIs. And we also basically extracted 300,000 PRCS from with our pDroid static analysis tool, and we analyzed and evaluated our work and generated the captions. Leclerc work is the baseline for us, and we compared our work and the translation with Leclerc, and we got close enough result, but we have some challenges, and the result is slightly worse. The reason is that Leclerc work was on a piece of code that generates just a statement about what the software does without a privacy behavior and privacy flavor. Having such data set is very complicated to have privacy flavor in it, and there's no such data set exists. So we decided to create our own annotator tool, which one of our undergraduate students is the developer of this tool, and it is available. You can use it. And we have like in-house annotators from our PhD students, master's students, and undergraduates that help to label the code segments that we extracted based on their privacy practices and purposes, so that we can improve our models and our result, our predictions. And we have an NSF grant under review and few work in progress that we are going to submit over the summer. And the next one, which is called FIN, and it deals with the IoT devices. We are collaborating with Dr. Kambiz Qazinur from SUNY University, and one of my graduate students, PhD student, with 2 of the undergraduates are working on this. We are evaluating IoT devices from different perspectives. What is the preference of the users? What are the risks of inferring personal information? And if there is inconsistencies between the applications and their privacy policies, we create risk reports, and then we provide a platform that the IoT devices can negotiate with users about their privacy policies and what they can collect. I'm not going to explain these formulas, but as I said, we are checking for inconsistencies and inference, and we have a set of approaches and formulas to identify that. This work also has been published on initial work, and we are working towards like the rest of it. The result that we have got so far is that with analyzing several IoT devices, you can create these privacy risk reports, which gives users more information about what is the risk if they want to use this IoT device in certain network, and they can make informed decision about their risk of privacy if they're using or buying certain IoT devices. We also submitted 2 grants, one NSF SAT-C, which is under review, and a Facebook grant, which is also under review in April. And we have 2 papers under review, so in progress to be submitted by end of summer. And the last one is related to privacy aid and LCO, which is a lattice-based contextual integrity analysis. And this is basically, as I said, it focuses on social networks, tries to identify and quantify the level of ambiguities that exist in privacy policies of social network. And we try to predict what is the likelihood of user misunderstanding of these privacy practices. We come up with a set of metrics, and we do a regulatory analysis, contextual integrity analysis, and some lattice space based on, for example, retention period, the collection, the level of sharing of with third parties, all of those things. And we rank these social network platforms based on their misunderstanding or ambiguities in their privacy policies. This project is in collaboration with Dr. Muller Worsdorfer from AI Seed Grant, and we have 2 4+1 students and 1 undergraduate students working on this project. So far, we identified 50 different social networks, and we classified them in 14 different categories. We evaluated their privacy policies, and we annotated 13 of them manually, and we are working on automating this process with unsupervised machine learning models. And we rank these social networks through how much are they privacy preserving. And we found out that YouTube and Facebook are the least privacy preserving, and they have more vague privacy policies than some of the smaller ones, for example, CaringBridge. Here we submitted 2 Facebook research grants. One of them got declined, unfortunately, and the other one is under review. And we are working on 2 papers to be submitted end of the summer as well. If you want to know more about these research, you can check my website. And thank you. I'll be happy to answer questions.
Thank you so much, Dr. Ganavati. We are going to hold questions until the end, and I will be happy to moderate amongst our panelists at that time. We really appreciate you sharing the results and progress of this research. Next, we're going to turn to Dr. Caitlin Howell, who is a professor in chemical and biomedical engineering with active research programs across a variety of topics, including biointerfaces, sort of nature or bio-inspired design, and a lot of sort of surface, whether it's cell surface or light and surface interactions. And I'm going to ask Dr. Howell to take it from here.
There we go. Sorry about that, everybody. I lost my mute button when I shared my screen, but thank you very much for that kind introduction, Saul. And I'm very happy to be here today and to present to you the work that we've been doing as part of our seed grant. It, of course, has this very long and complex title, so please allow me to give you a new one. That is how rainbows versus germs and how computers can help. So this little ball of proteins and RNA has been dominating our world for over the past year. And as part of it, it has really shifted our worldview and how we look at things. And particularly at the beginning of this pandemic situation, we all became very hyper aware of surfaces and their role in the transmission of disease. Now, this is particularly important because we live in a world where more and more often we were looking at shared surfaces that we are interacting with, airport kiosks, grocery stores. One of my personal favorites, airport restaurants, where you get to touch that nice little screen to place your order and then eat your food with those hands. And then finally, hospitals, where contaminated surfaces can spread antibiotic resistant bacteria and potentially produce a whole lot of pain in those situations with medically vulnerable people. So when we came to this, we said, hey, we really need a way in which the public in general can quickly and accurately assess whether or not a surface they're about to interact with is potentially dirty and therefore hazardous. So one of the easiest ways we thought to approach was actually using optical information. So we as human beings are very, very highly attuned to optical information. It's something that we use a lot and we process very well. So as Saul mentioned, in my group, we do bio-inspired engineering. We look to nature for the way that nature solves problems, and then we steal those ideas and put them to use for ourselves. So in nature, there are actually a lot of very good examples of using optical signaling to great effect. One of the most interesting, I would say, is what you see here in front of you. This is iridescent patterns created in nature on beetles, on birds, on butterflies, and even in some types of fruits. Now, the interesting thing about this type of iridescent coloring that is different from the usual pigment-based type of coloring is that this effect is actually produced through surface textures. This is something called constructive and destructive interference. When a ray of light hits this textured surface on the butterfly wing, for example, the light waves will be diffracted in a controlled and ordered way, which will allow them to interfere with each other constructively and destructively and produce that beautiful iridescent pattern that we see. So that is the natural solution. Let's talk about taking that and applying that to human problems. So it turns out that you can replicate this type of surface texture that is visible in nature and use it to do things for us. But so far, replicating this type of thing has been really kind of difficult. There you can see a bunch of examples of textures that we can replicate. But in general, you need to do this in a clean room with very, very expensive equipment and very highly trained people, which doesn't mean that you can produce a lot of this. So far, using this type of effect to do things in biomedicine has been relatively limited. But we have a solution for that: the Maine paper industry. So it turns out we have a Maine-based paper company, SAPI, down in Westbrook, that already creates a beautiful iridescent pattern. And they do this on paper making equipment, which means that they can produce this material in gigantic rolls, like that picture that you see there. So here we have the first step in being able to take this bio-inspired approach and use it for ourselves at scale. So how are we going to do that? Well, we wanted this material to be easy to understand and publicly available. So our hypothesis was that when we take this material that is being mass produced by SAPI on a clean surface, we are going to get a very controlled light interaction. When that surface gets dirty, though, we're going to notice a change in the way light interacts with that surface. Now, when we start to investigate this, we want to be able to do this in a way that is publicly available. So we're going to use smartphones, something that we all have, massive computing power in our pockets. And so to do this, we partnered with the VEMI Lab, who specializes in human technology interaction. And this project is really being led by my graduate student, Oshin Biswas, who's doing a fabulous idea. And our thought was, we want to develop a type of program that can be run on a smartphone, that you can use that phone to scan a surface, and it will return back either this is clean, it's okay, or this is dirty, you should probably consider finding a different one, or using your shirt. All right. So when we started originally playing around with this, we saw that just by doing some very fundamental taking of pictures with our smartphone and analyzing that color band, that we could see a difference between clean and dirty. You might notice in these pictures here that the clean peak looks a lot sharper and the amount of noise is much smaller compared to that dirty peak there, where you get the signal going all over the place and the peak is very spread out. But this is actually a really complex problem. And so to be able to really understand what was happening, we called in the big guns. Professor Sheila Adelatpur and her students Ramin and Saman are specialists in light interaction with materials. And so they started to help us understand what's going on and what information we could actually get out of the system. And it turns out that it's really, really complicated. What we see as a beautiful rainbow pattern is, in fact, a really complicated interaction of the light source, the refractive index, the type of contamination, the angle. So we're continuing to work at this, but at the same time, we are are going to start taking a different approach, one that is going to take into account all of these complex factors. And given what type of webinar you're in, you've probably guessed what that is: machine learning. So we are collaborating here with Professor Salome Seke and her student Josh Andel, and we are working to use machine learning to be able to take into account what is going on with these surfaces and return back to us an easily understandable result of clean or dirty. Now, I'm not a machine learning specialist, but Salome and Josh have told me that they are beginning to do this, and they have already taken the first step. They ran a bunch of our samples through what's called ResNet 50, which is a publicly accessible architecture, something that was very easy to do for a first attempt. This architecture runs our images through a bunch of filters, which can allow it to process the data more efficiently. So we provided this team with 53 clean images and 23 that were dirty with saliva, as well as 30 that were dirty with skin oil. All right, so we used 80% for training and 20% for testing, and we came back with a 59.1% accuracy. Now, this may sound not great, but actually it's really great because it's above what we would expect if it was just a random assignment of clean or dirty. And for those of you who are familiar with machine learning, you'll notice that this was only with 106 images. And so Salome and Josh said, you know, we need to have more images if we're going to do this effectively. And we had inadvertently in this process stumbled upon one of the major problems right now with applying machine learning in biomedicine. How do you generate enough information to accurately train your algorithms? So we tackled this problem head on. And with the help of a fabulous undergraduate, Theo Erickson, and RJ Perry, the manager at the VEMI lab, they actually built a system that would allow us to generate thousands of images in a reasonable amount of time. So what you are looking at right here is this instrument where you can put a smartphone and you have a controlled light source, and down there at the bottom is where you put your sample. And when we do this, we can actually generate a video of this material under this light source. And we found out that when we do this, because we can control the angle of the light and the angle of the smartphone, we can generate thousands of images actually relatively quickly compared to taking individual pictures. So we are now at the point where we're generating 3,360 images per hour under a lot of different conditions, and we are feeding that into the algorithm. Now, at the same time, Salome and Josh are working on now fixing up and designing an algorithm that is going to be more accurate and better based on what they learned from that first process with the ResNet. And in particular, we are very excited about this because this allows us to solve another problem that we see in image analysis and machine learning, and that is the amount of processing power that is needed. So generally, when you're analyzing an image, when an algorithm is analyzing an image, it is looking at the entire image, and you need a lot of processing power to process a big image. But in this technique that we are developing, actually the majority of the information is coming out of that rainbow stripe alone, right? So if we are in the process, Salome and Josh are in the process of designing this architecture to be able to focus down on only that piece of the picture that is actually giving us the best information. And through this, our hope is that we'll be able to reduce the processing power enough that it will be very easy to run this type of software on a smartphone. And of course, our entire overarching vision is to be able to produce a new type of algorithm, a new type of system that will allow you and those that you love to be able to go to anywhere where there's a touched surface and know if it's clean or dirty. So with that, I would like to thank my fabulous collaborators as well as all of the students who have been making this happen. And of course, the UMaine AI initiative for the seed funding that has allowed this all to go forward. And I will be happy to take your questions at the end of the entire session.
Thank you so much, Dr. Howell. I have to say, I particularly appreciated seeing all of the faces, including Optimus Prime, who've been involved in this work. I hope RJ Kelly has seen that. All right. Next, we are going to turn the floor over to Dr. Roy Turner. Dr. Turner is a professor of computer science, and today he's going to be speaking to us about their ongoing research in collaboration with image processing and bird counting. Is that correct, sir?
Yes, thank you, Saul. Let me see if I can get things set up here. All right, well, thank you very much for the introduction. What I'm going to be talking about today is some work that I'm doing with some others on context-dependent deep learning for seabird recognition and seabird recognition from drone survey imagery primarily, or in the future at least. All right, so working with several people on this, Cindy Lofton over in the Department of Wildlife Ecology and USGS, Salome, who you will see next and who you hear about a lot today, who's in our school, a couple of graduate students in ecology and environmental science, Logan Klein and Meredith Lewis, and Alex Revelo, who's doing most of the programming on the AI system, who's one of my graduate students. This project is what one of the researchers, one of the people is calling a transdisciplinary project. I kind of like that term as opposed to interdisciplinary. It's bringing together people from several different areas. It's actually part of a larger project that Dr. Lofton has had going on for some time. This is a focal point between some of the work that's going on in ecology and wildlife biology and some of the work that I'm doing in context research and deep learning in AI. And it allows us to bring together some of the deep research issues that we're interested in our own fields, as well as produce something useful for field biologists and others who are looking at seabirds and coastal environments. It's also beginning to spawn some research on how do you train people in a transdisciplinary, interdisciplinary team as well. The problem that we're addressing, at least from a biology perspective, is that seabirds are a bellwether of coastal ecosystem health. And we, of course, in Maine are very interested in the coastal ecosystem. But assessing the status of the seabird population is extremely difficult. They tend to be located when they nest. They're located on offshore islands many times. They're very remote. It's difficult to get to. It's time-consuming to count on the ground. It's also hazardous both to the researchers and to the birds as well. This has led over time to people using airplane-based surveys, flying over with cameras. It's still quite expensive, but it's less hazardous, although apparently that's the #1 reason for death in field biologists is airplane crashes. And it's much faster. It's done regularly by state and federal biologists with some ground truthing, people actually on the islands. The biology folks here also are moving toward a drone-based version of this that's cheaper, has better resolution because you can fly closer, have better cameras. You can also loiter and go back with the drones. And this picture of the drone here and then one of the people looking at it. And this is the difference between images between the airplane-based and some of the images you can get from the drone. But this has led to a new problem, which is, well, it's been in existence for a while. You have a tremendous amount of imagery to interpret. And what they have to do is go through these images and count the birds and identify the birds. This can be quite time consuming. For example, in one island had over 2,500 birds, for example. And this led two of our experts, our biology students, 14 hours each to count the birds on this one island. And we're interested in 274 islands. And you need to do this on a yearly basis. So you can see this can lead to quite a bit of time. And so obviously the solution they were looking at is automation with AI. And this is how I became involved with the group. Primarily, as you'll have heard and will hear, most of the AI recognition techniques are based on these things called convolutional neural networks. And we're interested as well, as some of the others, as Caitlin just mentioned, we're interested as well in finding pieces of the image that has some sort of meaning for us, in this case, the birds. And so we're looking at particular algorithms that are for image segmentation and object detection, as well as recognition. We want to find out where the birds are and also what the birds are. And there are lots of techniques for this, some of which I've listed there, one of which you saw in Caitlin's talk was that they're interested in the region of CNNs. And there's a couple of different ways of going about this, either proposing regions to look for objects or that might contain objects and then finding them, or this single shot, this one kind of network that finds where the objects are and identifies them at the same time. What we did was initially start out looking at a type of region convolutional neural network called mask RCNN. But unfortunately, we had some implementation problems. We're using our cluster that we got from a National Science Foundation MRI grant recently. And there were some problems porting this to the cluster. It worked most of the time, but occasionally we give segmentation faults. And between trying to debug someone else's code, basically, that we were adapting to the cluster and debug the cluster, it just wasn't worth it. And in particular, we didn't actually need the masks that it was giving us out. So we switched to a different network, one called YOLO, you only look once. The training time is, even on this very fast cluster, which has quintillions or quadrillions of operations per second, is still hours to days, 12 hours to several days to train one of these networks on the set of images we have. We have some recent, as of yesterday actually, results looking for herring gulls, this little guy, 92% accuracy when compared to the humans. That's the only baseline we have is the human tagged images. 83% for these guys, the great blackback gulls. Double-crested cormorants, 72%. Eiders over here, 69%. Terns, 52%. That doesn't sound great, but it is better than the best accuracy we've seen in the literature for similar sorts of things using an older version of the net. So we feel that this is going well, and it's also on some fairly recent training. We just began the training on this this particular iteration of this with some augmented data. This gives you an idea of what we're looking at. This is on the left, there are the raw images. On the right are the labeled images coming out of YOLO. These are some herring gulls. You see that it can be quite difficult to determine what things are in these images. You can probably spot these herring gulls down here, but in a different context up here, and we're going to come back to context in a second, a different context, this bird is extremely difficult to pick up. The system does it, but it's quite difficult to find there as opposed to, say, down here. And we can find that it's difficult to not think that might be a bird at first glance or some of these other buoys. And they can get quite crowded, these images as well. And here's the system coming up with again, some idea of those. Now, from an AI perspective, my personal interest is to try to improve some of the problems we have with these machine learning systems. The training time, as I said, can be hours to days for these systems, even on very, very high performance clusters. Ours here at UMaine is one of the state-of-the-art clusters that you can get right now. You need a large number of training examples, as Caitlin was just mentioning, that lead you to do things like augmenting the training data by manipulating the images and things like that aren't maybe not the best things that you can do, but that's all you can do in some cases. The networks themselves can be quite large. They can have billions of weights. And for example, YOLO itself, trained on the COCO image data set, I believe, from an image competition, just the data incorporated in that network is something like somewhere between 1/4 of a gigabyte to a gigabyte for just that one task. And the accuracy, as you saw, is still not quite good enough. You don't necessarily want to turn over bird identification to something that's going to miss 8% of the birds or whatever. Now, it's our belief that one of the reasons for this problem is that we're training across multiple different contexts. And so you saw these birds can look quite different in one context in the middle of grass, as opposed to a different context in the middle of rocks. We're also dealing with the fact that some of these objects don't appear in some contexts. You wouldn't expect to see great blue herons, for example, nesting on an island offshore on rocks. And yet the network has to learn that itself and has to detect that if it's doing across different recognition across contexts. They can't accept input from human experts because they're not symbolic. They're not able to deal with that kind of information. We've known for a long time that top-down predictions from context are extremely important in the human visual system, in animal visual systems. And we feel that this says something about what might be a route to improving the performance of these systems. So what this seed grant proposed is to bring to bear some of the work that I've done in the past on context-sensitive reasoning in other domains, in particular in autonomous vehicles and autonomous agents, and try to bring that to bear on this problem. And in the other system, what we're doing, I'm not going to go through this obviously, but basically take some sensor data, identify the context based on some knowledge we have about prior situations, fuse that knowledge together to provide information for the reasoner, which in this case was an autonomous agent. So applying this to the vision test, to the seabird counting test, we would see the same sort of thing where features of the situation in this case, the image or annotations of the image, or maybe some information given to the system from a person, bring to bear information and instantiate a neural network that fits the situation based on prior situations we've seen and trained networks in. When the situation changes, then let that very context-specific network operate in that context. But when the situation changes, then store whatever we've learned in that situation, if we've been in a learning mode, back into our memory, bring information about a network that fits the new situation and instantiate that to train in the new situation, so that you have at all times a tailored, highly tailored network for the situation. So what we proposed in Seed Grant was to identify some useful contexts and some contextual features for these situations, to begin the design of this, this context-dependent deep learning process, to conduct experiments where we would use our cross-context trained network that we're training at the moment as a control, and then use smaller networks. We believe we can use smaller networks trained in particular contexts and compare it to that for things like training time and accuracy, as well as getting some data on the size of these networks, as well as looking for ways to compress the networks. And that's where Dr. Seke comes in this. The current status is we've implemented YOLO 4. It's training even as we speak over on the cluster, hopefully getting better. We've developed via our capstone students in computer science, we've developed a tool for biology, the biology community to make use of our network when it's trained, regardless of what we do with the context-dependent stuff. With respect to the actual Seed Grant, the stuff that's actually proposed in there, we've done some of the preliminary work already throughout this past year. We've developed the YOLO process, the control network. We've got a journal publication so far that's in press. And what we plan to do this summer then is continue training YOLO to try to get it as good as it can be, run the experiments we mentioned with the other alternate networks, begin the implementation of CDDL as if this in turn indeed does produce good results, identify some promising compression techniques, and then look for follow-on funding sources and write the proposals. I'd like to thank you all for listening, and I'd like to thank the Seed Grant program for helping with this work and my collaborators as well. Thank you very much.
Thank you, Dr. Turner. And I'm sure no one involved in this project ever gets tired of saying YOLO. It's just available. And next we're going to hear from Dr. Salome Seke, who we've actually already heard mentioned in several of these projects. Dr. Seke is a professor of computer science here at the University of Maine, and she has active research programs in algorithm design and machine learning, data science, but also a particular interest in threat detection. And that's the subject of her Seed Grant and what we'll be hearing from her on today.
Thank you, Cyril. Thanks for the nice introduction, and I hope you all see my slides. I'm happy to be here, and thank you for the invitation. So first of all, let me introduce our team, who we are and what we do. So our team includes 4 PhD students, 1 master, and currently 1 undergrad researchers who is actively working on various projects. And in our team, we design machine learning algorithms. We study and investigate their theoretical analyses, and then we explore their application in various real-world problems. So my presentation today is a little bit different than my other colleagues who just gave such a fascinating talks. Instead of application of machine learning techniques, I'm going to talk about what's going on inside of these techniques. Of course, we run several projects in our lab, and today I'm just focused on the project that is funded by AI Initiative Seed Grant. Well, as we all know, deep neural networks have been used in a massive number of projects and in massive number of applications, from breast cancer detection, trajectory detection, and autonomous vehicles or robot navigations. So we obviously, over the past decade, we have seen that how complex they are and how well they perform in complex real-world problems. But when we use them, one of the aspects that we have to keep in our mind is about how robust they are. Deep neural networks massively have been used in decision making or task learning. And we have a complex task learning like autonomous driving or robot navigation. Therefore, we have a complex and complicated and deep neural network. So when we deal with this neural network, we have to make sure that they are enough robust in adverse environments, for instance, adverse weather condition. While we are driving our autonomous cars, we need to ask them that if they perform well when the weather all of a sudden changes. And this type of the problems. So these type of the problems are called adversarial machine learning. And today I'm going to talk about them more. So it turned out that adversarial machine learning or deep neural networks are vulnerable to perturbations. So if your input images are perturbated or they have some noises involved, then they fool your neural network. In other words, your neural network is vulnerable toward this type of the input data. So it turns out that if you have some noisy input and you feed it into neural network doesn't make accurate decision. If your neural network is robust enough to, even with such examples, still can make an accurate decision, then you can call it your network is robust enough. Of course, there are some defense mechanisms that can deal or help to your network to be able to deal and handle these type of examples of these type of attacks. So this observation was made throughout a couple of last years, but then what if we use this, even if our input image is not noisy, but what if we intentionally manipulate the input data and make it adversarial example, so then our network becomes robust enough. So then now the problem is flipping out, and now it's completely different. Even if my input is not noisy, I generate adversarial examples. So adversarial examples are, in fact, they are inputs to your machine learning models, including deep networks, that an attacker has intentionally designed to cause the model to make a mistake. So we intentionally challenge our neural networks by these adversarial examples. There are different forms of adversarial attacks. And of course, based on various attacks, there are various defense systems. For instance, if you add some noises to your input data set, you generate adversarial example. Or if this additive noise is added into input from different angle, you generate adversarial example using deep fool technique. Later on, there are even more advanced mechanism to be able to generate adversarial examples. For instance, if you specially transform your input, you can generate this type of threads. And also recently, there is a new thread model, which is not even additive form. Actually, you perform and you map the entire input using a map function, and then you generate adversarial examples. So now, based on this, which is a very short list of tons of adversarial or threat models out there, you implement them defense mechanism. But there is something missing in all these threat models. All of them, when they adversarially train the network on these examples, they train the entire network. The main question that at this point we had, and we wanted to tackle this problem, was what if we only train adversarially a subnetwork and then imply the other subnetwork to be robust based on first training system? So this means that, of course, when you train the entire network, you computationally making your training process complex. However, if you train only a sub-network, you can take advantage out of it. The first advantage would be the time, so it would be much faster. So we actually propose an algorithm which guarantees the sub-network robustness based on adversarial training the first sub-network. So there are two mechanisms that you can follow once you face with the threat, right? You can adversarially train the entire network, and of course you have your own test accuracy. But you could also, we propose that you could adversarially train the first half of the network and then imply that the second half of the network is robust as well, with at least the same accuracy. But of course, there has to be something else involved. And it turned out that we could show if these two networks or layers in the second network are mutually dependent to the layers in the first network, then we can guarantee their robustness. But the question was, what are those mutual dependency measures? In this project, we started with two mutual dependency measures. First, mutual information, which is a probabilistic measure, and it's an information theoretic measure. It has been shown that it helps a lot, and it's a good tool and efficient tool for dependency. And we just showed that if we have our layers in the subnetwork 2 be mutually dependent and have a high mutual information with the layers in subnetwork 1, then we don't need to train adversarially the second subnetwork. It's already robust. Not even with the same accuracy, sometimes even outperforms the method that you are training the entire network adversarially. In addition to that, we were wondering what else we can use here as a dependency criterion. And it turned out that if layers in second layer, and if layers in second network, subnetwork, are linearly combined with the layer in the first network, you can still support and guarantee the robustness for subnetwork 2. So this was very interesting to us because now we didn't need to train the entire network adversarially. We just needed to train a subnetwork and then guarantee the second subnetwork. In order to validate our theoretical analysis, and we develop a long list of theoretical analysis here, we want to see that how our model performs on well-known networks. So of course, we use some common CNNs, AlexNet, ResNet, ResNet 18, ResNet 50, and it turned out that our mutual information-based algorithm not even meet the baseline, it even outperforms 2% the baseline. This 2% in this type of the complex problems is very high improvement. So for linear combination for AlexNet, as you can see, we could see that we just meet the baseline. Our algorithm was validated on ResNet 18 using mutual information based dependency measure and on ResNet 50 as well. But in the first experiments that we tried, our subnetwork 2 contain only single layer, and that's a good start, but that's not enough. The next question is that how many layers we can support in second subnetwork. If we adversarially train the first subnetwork, how many layers in second subnetwork are supported? And we know that they are robust, and we don't need to be to adversarially train them. We tried for the second layer, 2 layers, and we showed that 2 layers are guaranteed. Not even guaranteed. Also, in some networks like ResNet 18, we saw that if our second subnetwork contains 2 layers, so the size is 2 layers, we even outperform about 3% the baseline. So that was a great achievement for us. Once I saw this number, thanks to my student Jovan, and I was like super excited. All right, so of course the next question is how many layers? Up to how many layers we can go? And the good news is that we increase this. The mutual information-based algorithm, in fact, showed that sometimes it's even 4% can guarantee, which is can outperform, which was very good news. But still, this isn't going up to here. The achievement was fascinating, and we even were planning to submit it to NIPS this year, but we decided to extend the experiments a little bit more and submit it to the next venue. So based on this, there are still a lot of other experiments that we are excited to try. For instance, we're excited to try, Cypherton is already a big data, but we are planning to do it to implement these techniques on ImageNet, which is millions of data. And I am optimistic that hopefully we will get exciting results. But aligned with this project that my student Jovan with our external collaborator from National Lab, Ted, have been working. Aligned with this, I was working with Sepid and Tom and RJ from Vemilab on an application of these all techniques. So as I explained in first slide is that when we do object detection, of course, a big question for us is how our object detection is robust enough or perform well when we have adverse weather conditions. So we know that if we use the fusion of multimodal sensor streams like camera, LiDAR, radar measurements, these all, a combination of these all measurements play a key role and critical role that big AV companies have been using that in order to detect objects in robots and autonomous vehicles. So we started to only focus on camera base because the architectures that are designed with these big companies are extremely complex. So we first started on first branch of the architecture, which is designed by Mercedes-Benz and published in CVPR 2020. So we started with that, and Sepid and Tom with data that RJ from Vemilab was helping us. We tried to implement this on PT dataset, which is a video-based object detected well-known dataset, and they could implement the algorithm. Of course, this is a very ongoing a long-term plan, and as a small piece of it, we could see some interesting results. But of course, we need to involve camera, LiDAR and radar measurements in order to make sure that we get the optimal performance. However, in addition to this, we are planning to include the adversarial robustness algorithm that we designed in phase 1, and hopefully we use it someday in near future on this architecture. As a long-term plan with our team and external collaborators, hopefully we will team up with some good companies, and we will be able to collect our main data, because we all know that winter and adverse and severe weather is a big deal. I would like, this is, as I said, very ongoing project, and this is going to take a while. But we are very excited about this, and we are very thankful to our external collaborators and AI Initiative Seed Grant that supported our students. And I am happy to take any questions.
Thank you so much, Dr. Seke. And we have several minutes left. These have been an exciting series of presentations that sort of demonstrate some of the breadth and depth of AI relevant research that's ongoing at UMaine. As many of you on this call are aware, this is an area of sort of growing activity and investment for both UMaine and the system. And I do see we have colleagues from across campus, other system campuses, and presumably some folks I don't know from points farther beyond. So we have a couple minutes left for questions. These can be for any of the panelists about the specifics of their research, or about the actual process. What we've heard described were pretty rich collaborations. And I have a couple that are waiting here in queue that came in during the presentations. The first is actually for Dr. Howell, and it's a question about environmental lighting and ambient light, or if you needed to work in a dark space.
That is an excellent question. So right now, because this is a new concept, and with this seed grant, we are really building the capacity to be able to expand off of this. We are using controlled lighting in a dark room. That is just to allow us to optimize things, prove the concept out, and identify where the problems are that we can fix. However, once we have the system to be able to generate the massive amount of images and the beautiful architecture that Salome is building, then we will be able to expand this out into different types of lighting conditions. And the idea is to use this as a starting point and then go on from there. So for airports and grocery stores, we'll be looking at fluorescent lighting. For other applications, we might be looking at outdoor lighting from different angles. So there's a lot that we can do with this, but where we are now is just the start.
Thank you very much. And for directly addressing that question, the next question is for Dr. Turner, and I think Dr. Ganavati could also speak to this, which if you could identify the challenges or hurdles that arose in collaborating sort of across the disciplinary gap described in your project.
The problems that typically arise are people just speak a different language in different areas, that terms mean something different, than that people need to know something about the other person's field. And we've been very lucky in ours in that one of the graduate students, especially in wildlife ecology, is very interested in computers and programming as well, and took I believe Dr. Yu's machine vision class and things like that. And so it's kind of just being familiar enough with the other person's field in order to actually communicate with them, to know what you need to ask and stuff. I think that's, it's an interesting process.
I agree with Dr. Turner about the different terminologies, especially when you work with lawyers and computer scientists, and they talk like completely different terminologies. And basically, that was one of the biggest challenges we had, and also that there's so many like points that you can basically do in these type of projects, looking at like different privacy regulations, and then there are several different types of emerging technologies. Each of them bring different challenges, and how to narrow down the focus of a project and making like the goal, like more tangible goals and immediate goals. That was another challenge that we had. And of course, like having our PI being extremely busy on other projects, that also like delayed a little bit our progress.
Thank you very much. And I'm going to actually, and I apologize, we're going to leave a question open that came in from Nicholas Jacobs, and I'm going to ask Dr. Seke to follow up if that works. I just forwarded that question along in a private chat. And because we are running out of time here, turn the floor back over to Dr. Abedi.
Thank you very much, Saul, for moderating the session, and thanks to the Office of Research Development for managing these seed programs. I would like to thank all the speakers for the great presentation and great works, which was definitely more than a seed grant kind of level of research activity. Also, I want to thank the crew in the background who were running the show for us. So our captioneer, Nicole, and also our event manager, Mindy Pelletier at the UMaine AI Initiative. I also want to make sure that I thank the Office of Vice President for Research for funding these seed grants. And again, thanks to IEEE at different parts of the world for sponsoring this event. And The last thing I would mention is that this is the last webinar that we have for this semester. So we'll take a break in the summer, and we'll come back in the fall with a series of new webinars with specific topics with program directors and academics and industry people. So stay tuned for our future webinars. And again, thanks everyone, all the attendees, for joining us. Feel free to check our previous webinar recording as well as this one if you missed part of that on our AI website. So you just search for UMaine AI and you will get to the videos. Thanks again, everyone, and have a great day.